Good morning. I'm Tsimafei Lazouski, and today my thesis partner, Kohta, Erdos, and I will be presenting our thesis titled Development of a Simulation and Controls for a Low-Cost Buoyancy-Driven Underwater Glider. Our principal thesis advisor was Professor Michael Martin. Before we begin, we would like to thank some people who assisted us with this process. First, we would like to thank Professor Martin for his continual guidance, patience, and active engagement throughout the entirety of this thesis. Our reader, Dean Warner, and our editor, Professor Scott, for their thoughtful and detailed comments on all of our submissions. Also, Professor Royce and Pat Doherty for letting us use the Robinson Model Basin, and our classmates, Katie Zhang, Will Calley, Evan Kawabata, and AJ Mills, for helping us with testing. Now, we will move on to the objectives. The objectives of this thesis were to develop a mathematical model for a glider simulation, to enhance the controls and increase the computational power of the Orca glider built by Gabe Allen and Natalie Webb in 2023. And finally, to develop the simulation against the controls. For this presentation, the outline will be as follows. First, we will go over the background for this project, in which we will discuss buoyancy gliders and the past thesis. The background will be followed with the discussion of the physical modifications made on the past thesis and the theory that supports our thesis. Then Kohta will take over as he will talk about the simulations, the testing, and the conclusions made on this project. All of this will be wrapped up with some recommendations for future work. Now, you may ask, what is a buoyancy glider? Buoyancy gliders are a type of marine robots that use buoyancy regulation to propel themselves. The propulsion is possible thanks to the lift force that is perpendicular to the glider wings. In the figure, you can see a glide cycle of a generic glider. The glide cycle closely resembles a sinusoidal wave. When first in the water, the glider starts flat at zero trim. Then it starts taking in ballast and moving downward and forward. Once it reaches the desired depth, it starts deballasting, moving upward. At the next peak, the glider starts repeating the ballast-deballast cycle, continuing the cycle. For our thesis, we are controlling this exact pattern. Now, knowing a bit more about gliders, you may ask, why are they of any interest? Buoyancy gliders can be deployed over long ranges of time and extended periods due to their energy efficiency. Because they have no propeller and glide at speeds of around 2 meters per second, they have a low disturbance on the surrounding environments. Also, they are especially well suited for challenging environments where larger vessels or human divers cannot access. Their flexible payload and sensors allows them to be used for a wide range of applications, and they can collect data on water properties, the surrounding environments, or marine biology. For these reasons, buoyancy gliders are used for a wide range of data collection applications across the globe. Last year, Gabe Allen and Natalie Webb developed a Webb thesis in which they designed, built, and tested an underwater glider. The glider was equipped with basic roll, pitch, and ballasting capabilities. It had a time-based control loop to ballast and deballast for testing purposes. Having a time-based loop means the glider had no way of making dynamic adjustments based on its orientation. However, more importantly for our work, the thesis had a solid foundation for developing more complex controls. The glider was equipped with an Arduino Uno and reserve room within the body of the glider for additional hardware. This was all supported with good documentation of the work complete. Following up on the past work, we fulfilled some recommendations. First, we addressed the porous end cap problem. Previously, because of the porous nature of the end caps, water slowly leaked into the end caps, which affected the weight balance of the glider. To battle this, new end caps were printed and sealant was applied to prevent the leaks. One of the new end caps can be seen in the figure to the right. Additionally, smaller internal parts were printed to accommodate the increased needs of our thesis. The new internal parts were used in the computing hub seen in the figure. A Raspberry Pi and Arduino were added to increase the computing power of the glider, and an internal measurement unit was added to gather the glider orientation data. Following the physical modifications, the glider got a new look. However, after the modifications were made, an evaluation of the glider capabilities was necessary. We quickly found that the glider was no longer heavy enough to submerge, which led us to carefully reweighing all of the glider components and adding lead ballast. Along with the design changes, the control capabilities had to be evaluated. It was found that the shift in the longitudinal center of gravity was only 0.2 inches, while the shift in the transverse center of gravity was 0.2 inches. Continuing the discussion of the shifting centers of gravity, the general arrangement can be introduced. The glider's center of gravity is the key motion parameter, and it can be controlled in two ways. First, through the water ballast pump in the forward end of the glider. Second, through the shift of the rotational weight in the aft end of the glider. For reference, the computing hub is towards midships. With the physical model introduced, we can move on to the equations needed to describe the motions of the glider. First, we will define the coordinate systems used for the development of the motion equations. It is common practice for marine vehicles to use two coordinate systems, one of which is the Earth fixed system, in which the motions of the object relative to our planet are tracked. Note, the positive z direction is downward, and the x and y axes form the horizontal plane. The other coordinate system is the body fixed system. It replicates the conventions of the Earth fixed system. However, it is used to locally track the motions of the glider. Using the installed IMU, it is possible to capture the motions of the glider in 6 degrees of freedom, which can be seen in the figure to the right. Note, the B subscript is used to indicate that we are working with the body frame of reference. In the figure, the positive x direction is towards the bow, the positive y direction is starboard side, and the positive z direction is downward. You can also see the respective translational speeds in those directions, u, v, and w, along with the angular velocities about the axes, theta, phi, and psi. To understand the forces acting on the glider, a free body diagram can be used. In the figure shown is a schematic of the glider. The axes of this diagram are in the bottom left corner. The positive x direction is to the right, and the positive z direction is downward. With that established, we can go over the forces. Highlighted is the buoyant force acting in the negative z direction. Another force acting upward is the lift force, which is perpendicular to the glider wings. The final significant force is the weight force, acting in the positive z direction. As it can be seen from the free body diagram, there's only one force that contributes to the acceleration of the glider in the positive x direction, which is the lift force. However, using a careful combination of these forces can allow the glider to propel itself, and this motion can be controlled through the shift of the internal weights of the glider. Working with two coordinate systems requires a means of translation from one to another. To accomplish this, the Euler's rotational theorem was used. To follow along with what is to come next, in the top left is a summary of all of the variables defined previously, along with a familiar schematic to the right. Now, to translate the body-fixed linear motions, a rotational matrix R will be used, and it can be seen to the left. After a full expansion and simplification, it takes the following form. The rotational matrix can then be used to define the linear motions using the following equation. On the left-hand side of this equation, you can see the Earth-fixed velocities, and on the right-hand side of the equation, you can see the body-fixed velocities. The final form of this translation is as follows. Note, in this equation, the C's represent the cosines and the S's represent the sines. Fortunately for everyone in the room, the fun does not end here. Now we will loop through the angular motions. A matrix will likewise be used to translate the angular velocities from the body frame to the Earth frame. The translation process is similar to that for the linear motions, and the final product can be seen in the bottom right. After looking at the kinematics of the glider, we can consider the body's geometry and mass properties. Below is the fundamental relationship that determines our ability to predict the vehicle's motions. On the left-hand side is the vehicle force moment equations. On the right-hand side of the equation is the sum of all the hydrostatic, hydrodynamic, and external forces and moments. In the figure to the right, you can see the Snamey motion convention used for the left-hand side of that equation. For the right-hand side of the equation, you can now see the hydrostatic formulations, in which W represents the weight of the glider, and B represents the buoyant force acting upon the glider. And now are shown the hydrodynamic forces and moments. Open source hydrodynamic coefficients from the underwater vehicle built by the post-naval graduate school was adapted to develop the equations of our glider. This was done due to the availability of the information and the provided geometric scaling factor methods. While a lot of equations were developed in our thesis, and a lot of variables defined, the final product comes down to the transfer functions and the Laplace domain. These transfer functions can further be used in software to simulate the glider motions. In the figure shown is a sample set of the transfer functions for a glide cycle in which the angle of attack is 10 degrees. The key takeaway from this set of equations is simple. It all comes down to the location of the center of gravity. xg is the notation used for the center of gravity, and as it can be seen, it drives the pitch velocity, the angle, and the depth functions. These transfer functions were then used to make the simulations and develop controls. And now Kohta will take over the presentation as he will talk more about this process.
Thank you, Tim. To control our glider, we apply the principles of control theory to analyze our system. The objective of control theory is to use applied mathematics to develop a model which regulates the system. A control system, such as the one shown on the block diagram to the right, regulates the process variable to a given set point, which is the target value for the process variable. The plant in the control loop represents the physical environment the system exists in. The controller determines what actions are being taken based on the set point. A control system must also account for what disturbances and noise factor into the control loop and how sensor data is processed. Since this system incorporates feedback from a sensor, it is a closed loop system versus an open loop system without feedback. In the case of our underwater glider, an example of a control system we used was for controlling the depth of the glider. The process variable would be the current depth of the glider, and the set point would ensure the glider does not exceed the maximum rated depth. For the control of the buoyancy glider, we implemented many proportional integral derivative, or PID, controllers. As the name implies, PID controls use proportional, integral, and derivative components of the difference between the feedback and set point. PID controls are used to create accurate and responsive corrections while minimizing delay and overshoot. In the diagram, R is the set point, E is the error, U is the control input into the plant, and Y is the output. KP, KI, and KD are three gain terms which must be tuned for the system's specific application and environment. To the right, you can see an example response of the glider's pitch being controlled. The angle in degrees on the x-axis is plotted against the time in seconds on the y-axis. When tuning our control systems, we primarily focused on minimizing the overshoot of the set point and the steady state error. The time until the system reached a steady response, or settling time, was also considered, but this played a lesser role since the actuation times of the glider were slow. PID tuning was done in the presence of errors to confirm that the glider can operate in various conditions. MATLAB, an abbreviation of Matrix Laboratory, is a programming and computing platform with many functions that were useful for creating, tuning, and testing our control systems. Simulink is a model-based design module of MATLAB, which can model and simulate dynamic systems. The combination of the two software is especially powerful for our application, since MATLAB can directly compute transfer function equations, which are then used within the Simulink environment. These functions used in the simulation were based on the equations of motion Tim derived earlier, and the characteristics and environment of the glider. To greatly increase the controls capabilities of the glider, an Inertial Measurement Unit, or IMU, was installed on board. This IMU outputs constant readings for 3 degrees each of rotation, gravitational acceleration, and absolute acceleration for a total of 9 degrees of freedom. The IMU also monitors the state of each reading's calibration. To obtain useful and accurate readings from the IMU, the outputs were processed and filtered to filter out background noise and damp, sharp excitations. The IMU, the IMU was connected to one of the Arduino Unos on the glider, which both processes the IMU data and tracks the calibration state. When the system first starts up, a short calibration dance consisting of figure-8 motions in different orientations was done. This ensured that the system began calibrated, and the state of calibration was tracked with an LED light programmed to indicate the calibration stages. The table shows the various calibration stages, where the LED goes from off to blinking to solidly on as the IMU is further calibrated. This feedback helped us in all of our IMU and glider testing to ensure that we were feeding the glider correct data. The main controller and decision maker on board the buoyancy glider is the Raspberry Pi. This is a single board computer operating on Linux, which has much greater functionality than the two Arduino Unos, which each handle smaller processes. The Arduinos are microcontrollers which operate on a variant of C++. One handles IMU data and the other sends commands to the motor controller and is connected to an adapter which can wirelessly be turned on or off using this garage clicker. Here, the different components are shown with their connections to each other. The Raspberry Pi is connected to both Arduinos, which are also each connected to different components they control. Of note is that the IMU Arduino is connected and powered by a single serial data connection to the Raspberry Pi with additional general purpose input-output or GPIO pins. GPIO pins output either an on or off signal and must be configured to either send or receive a signal. The serial data connection is used to send high-speed process IMU data. The motor control Arduino is connected with 8 GPIO pins to the Raspberry Pi. Here, the types of communications that each component sends to each other is shown. One thing to note is that the IMU Arduino on the left only sends IMU data to the Raspberry Pi, while the motor control Arduino communicates in both directions with the Raspberry Pi. This Arduino receives motor commands to set the state of the various stepper motors and also communicates whether the wireless adapter signal is on or off. This wireless on-off signal is the means by which we are able to communicate with the glider while the hull is sealed for testing. To be able to test all the different functions of the glider with only one on-off input, a sophisticated testing loop was developed. Logic in the Raspberry Pi was coded to ensure that we could put the glider in the water and not have to disassemble it between different tests. Here, the block diagram of a single branch of the testing logic is shown. This branch is specifically for the roll test. It also makes sure that the glider returns to its default home position before running a test. This loop will continue into a similar loop with a different test once the roll is completed. Here, the complete block diagram of the testing logic is shown, with all three of the roll, pitch, and dive test loops included. The glider will move on to an idle state before the next test after completing the previous test. This function overcame the limited input we had into the glider once it was in the water. Here, the overall control loop running within the Raspberry Pi is shown. This replaces the timer-based loop that the glider ran on beforehand. The control loop begins by setting up the connections and preparing to record data at each time step. After time step information and inputs are updated, the control logic determines how the glider should proceed and calculates the state of each of its motors using control equations developed in Simulink. Additional logic is included to ensure the glider does not exceed the physical limits of the motors and motions not included in the simulation. From here, the appropriate outputs are updated and the state of the glider is recorded with its time step since startup. Proper time accounting plays an important role in the operation of the controls for several reasons. First, the states and commands issued within the glider must be properly recorded to evaluate how the glider is responding to its motions. Second, good timekeeping is needed to properly make use of the IMU data for integration. And finally, the exact positions of the different motors are not tracked by limit switches, meaning over-actuation can cause damage to the glider components. As such, the state of the ballast cylinder and weight tray are tracked using the last given command and the time since that command. This also requires that the glider is reset to a known position upon startup. Excuse me. To rapidly test our controls software out of the water, we developed a software in the loop or SIL code in Python. This used a simplified model of the glider to test different controls functions. The glide cycle SIL test consisted of a two-dimensional test of how the glider controlled its depth. The different forces on the glider were developed based on the state of different motors from the state of the glider in the previous time step. State variables in the SIL test included position, velocity, and acceleration for the glider, as well as the positions of each motor. For our testing in Webb's Robinson model basin, both the control software and the single button testing logic behaved as expected. The controls successfully actuated the ballast motors and pitch motors at their design speeds. The issue was that the weight tray was unable to rotate during testing. Even when on the bench, everything was functioning as normal. The weight tray was not able to rotate due to the tight clearance between it and the hull tube. Here you can see the cylindrical tray fits snug within the hull tube and requires more torque than the motor can produce, even with more than it can produce in the water. Because of this, the physical testing could not be completed for the rolling tests. To verify the accuracy of the IMU data outputs, several rounds of bench testing were conducted. The culmination of the testing and tuning of the IMU data processing was the full motion test, which took place in the Boise-Bollinger Courtyard at Webb Institute. The control system was reduced into a portable form consisting of an IMU, Arduino, Raspberry Pi, and battery bank, and walked around the rectangular perimeter of the courtyard, where the star represents the start. The resulting path to the right shows the X and Y position of the IMU both in feet plotted against each other, with the start at the origin as the starting point. The plot shows that the data processing of the IMU was mostly effective, especially at the low speeds expected of the glider. Of note is that the Bollinger Courtyard path was measured to be 100 feet by 70 feet, while the path of the IMU is 105 feet by 68 feet. The IMU data is much more accurate in the first stretch of the run and accumulates small errors that carry forward in its reckoning. For the simulation of the glide cycle, the test space was simplified to a 3-degree of freedom model in the XZ plane. The AUV controls were set to run the glide cycle, controlling for a design depth of 30 feet. In the results, at steady state, the x-axis is the runtime in seconds, and the y-axis is the depth of the glider in feet. In this ideal scenario at steady state, the glider was able to control its depth, not overshooting the target depths of 0 and 30 feet. The glider controls were tracked over this test period and changed states and moved as expected in response to the glider motions. While a scenario with 0 lateral motion of the AUV is not typical, this test demonstrates the effectiveness of the control system for the AUV's glide cycle. The result of our testing was that the glider demonstrated the end cap and computing tray modifications made to the buoyancy glider were able to achieve their purpose. A mathematical model of the glider was developed and aided greatly in the predictions needed to add controls to the glider. The addition of the IMU was shown to be able to give the glider reasonably accurate position and orientation data. Where the buoyancy glider failed to perform in water was in achieving any roll motion due to the excessive friction between the weight tray and the hull tube and roll. The glider responded and performed test procedures as expected, even though the motor actuation was not enough to move the weight tray. The control logic for PID control loop, as well as the overall system loop, proved to be robust enough to run, execute testing procedures, and record a comprehensive data log over the course of each testing period of over 45 minutes. We have a few recommendations for future work for students who are interested in working with AUVs. Rebuilding the weight tray section and running full dive tests for the glider would be the most direct continuation of this thesis. Another type of AUV, another type of AUV could be designed with the controls platform as a starting point. For example, an AUV with a propeller could use the computing and IMU platform while still having its own unique and interesting challenges. Much of the logic and IMU computing capabilities could be transposed into a different system by changing the parameters to match that new system. Alternatively, the simulation and testing results could be used to design a theoretical Orca 2 glider. This would best be done by changing the variables such as the amount of ballast and the distance the weight tray is able to move. Also, it would be beneficial to make use of the glider's simulations before construction to verify the design. Thank you for listening. And at this time, I would like to invite Jack Otto up to present his thesis. Please hold all questions until the end of his presentation.